Today I want to look at the Fibonacci sequence mod M and discover its periodic nature and say something about the period of the sequence. So we'll first define what a periodic sequence mod M means. Then we'll look at the Pisano period. That's the period of the Fibonacci sequence mod M. We'll take a look at the Fibonacci sequence viewed as a sequence in a finite field. We'll look at the relationship between the Pisano periods and orders of elements, and then look at the matrix point of view of the Pisano period. And then finally I want to make some estimates for these Pisano periods. Okay, so what is a periodic sequence mod M? So a sequence of integers a sub n is said to be periodic mod M if for some positive integer k, a sub n plus k is congruent to a sub n mod m for all natural numbers n. So it has a repeating cycle of length k, and then the minimal value of k for which 1 holds is called the period of the sequence. So for example, if I'm looking at the arithmetic progression 1, 5, 9, 13, 17, 21, 29, and we look at this mod 6. So mod 6, 9 becomes 3, 13 becomes 1, 17 becomes 5, and so on. We see that the sequence keeps repeating 1, 5, 3, 1, 5, 3, 1, 5, 3, and so we have a repeating cycle of length 3, so we call it a periodic sequence with period 3. Okay, here's the Fibonacci sequence, and let's take a look at it in mod 2 and mod 3. There's a couple ways we could do this. We could just take the original numbers and reduce them mod 2 or mod 3, or we can look at the defining relationship, and this is generally a much faster way, and just say that the nth Fibonacci number is congruent to the sum of the previous two, mod m. So if we are looking at the sequence mod 2, we've got even, odd, odd, even, odd, odd, even, odd, odd, even, odd, odd, and very quickly we see that it has period 3. So it's periodic with period 3. Or if we look at the Fibonacci sequence mod 3, let's go ahead and use the defining relationship here. So 0 plus 1 is 1, 1 plus 1 is 2, 1 plus 2 is 3, which is 0, 2 plus 0 is 2, 0 plus 2 is 2, 2 plus 2 is 4, which is 1, and so on. Now if I'm looking for the minimal cycle, what am I really looking for? So the sequence starts with 0, 1, and two terms of a Fibonacci sequence determine everything after it by the recursion relationship. So all I do is I go down the sequence until I see a 0 and 1 repeat, and there it's repeating right here. And so from this point on, we're going to get repetition. There's our repeating cycle, so periodic with period 1, 2, 3, 4, 5, 6, 7, 8. So that leads us to ask, is the Fibonacci sequence always going to be periodic mod M? Okay, we can look more generally at any linear recurrence. So let un be a sequence of integers satisfying the linear recurrence right here, where a and b are fixed integers. Then we claim for any positive integer m, the sequence un is periodic mod m with period at most m squared. So in particular, the Fibonacci sequence would be periodic with period at most m squared. So let's see if we can prove this. Okay, so for any n greater than or equal to 2, we've got that un is congruent to a un minus 1 plus b un minus 2 mod m. So what I'm going to do is consider the m squared plus 1 ordered pairs u0, u1, u1, u2, u2, u3, so all consecutive pairs of numbers in the sequence. And I want to view these ordered pairs mod m. So there's only going to be m choices for the first entry, m choices for the second entry. And I've written down a collection of how many ordered pairs. Now there are m squared plus 1 ordered pairs in this collection, and there's only m squared distinct pairs mod m. So by the pigeonhole principle, two of these, at least two of them, have to be the same ordered pair mod m. Well, what does that mean? So that means there's some I less than j such that this ordered pair ui plus 1 matches this ordered pair uj plus 1. In other words, that ui matches uj and ui plus 1 matches uj plus 1. Well, these are recurrence sequences, so every term after these two, the ui and the ui plus 1, is determined by those two. So it's going to follow that ui plus any number L is congruent to uj plus any number L. And you can do a formal proof by induction there. So let's put n to equal I plus L and k to be j minus I, which is positive since j is bigger than I. Then the relationship up here just becomes un on the left and then j plus L on the right becomes what? Well, L is n minus I. So it becomes j plus n minus I, and j minus I is k. So this is k plus n. So this becomes un is congruent to un plus k mod m for any n greater than or equal to 0. So it's periodic with period at most k, and k is j minus I, so k is at most m squared. So we get periodic with period at most m squared. Now, for the Fibonacci sequence, we give the period a special name. So the period of a Fibonacci sequence mod m is called a Pisano period, denoted pi of m. The period is named after Leonardo Pisano, better known as Fibonacci. So we'd seen earlier that the Fibonacci sequence mod 2 was periodic with period 3, and mod 3 it had period 8, so pi of 3 is 8, and by the previous theorem pi of m is at most m squared. Okay, we want to improve on this bound right here. So let's just study it more carefully. Okay, let's focus on the Fibonacci sequence mod primes. So I'll let Fp be the finite field in P elements, and let's look at the Fibonacci sequence as a sequence of elements of this field. So 0 and 1 are in the field, and then every subsequent term in the sequence is just the sum of the previous two. And we want to look at the periodic behavior. So what we do is go through the derivation we did back in the first section on Fibonacci numbers, where we viewed them as integers, and we came up with this formula in terms of the golden ratio. So you get exactly the same derivation, provided we're working in a field where p doesn't equal 2 or 5. So we can talk about the inverse of 5 and the inverse of 2. So here phi bar is the golden ratio viewed as an element of Fp, or as an element of a quadratic extension of Fp if need be. So what does this formula really mean when we're working in a finite field Fp? Well, two things are obvious. The 1/2 here really just means the multiplicative inverse of 2, which is okay. And when you have a 1 over 5, that really just means the multiplicative inverse of root 5. But what does the square root of 5 itself mean? So there's two considerations there. So the square root of 5 denotes some value lambda with lambda squared being 5. So if 5 is a quadratic residue, mod p, then there will actually be some element in fp that satisfies this equation. And so we get that phi bar, this golden ratio here, is an element of fp. If 5 is a quadratic non-residue, then the square root of 5 doesn't belong to fp, and you have to go to a quadratic extension, which is fp squared, the finite field and p squared elements. And that's where phi bar is going to be living. So phi bar here is an element of fp squared. Theorem. Suppose p is an odd prime not equal to 5, so those were the two cases we had to stay away from. If p is congruent to plus or minus 1 mod 5, then the Pisano period is the least common multiple of the order of the golden ratio and the order of the conjugate of the golden ratio. If p is congruent to plus or minus 2 mod 5, then the Pisano period is just the order of the golden ratio. But this time we're viewing phi bar as an element of the finite field and p squared elements. So to begin the proof, we just treat any prime that's not equal to 2 or 5. And what does it mean to study the periodicity? So to be periodic, we want fn plus k to equal fn in the finite field fp. So you're taking the Fibonacci sequence and you're viewing the terms as elements of the finite field fp. Well, by the formula on the previous slide, fn plus k is 1 over root 5 times this quantity, and fn is 1 over root 5 times this quantity. So you just cancel the square root of 5 on both sides, and we get this identity. Then rearrange the equation. So put phi bar to the n onto the left, and put the phi prime to the n plus k over to the right. Factor out a phi bar to the n, and you're left with phi bar to the k minus 1, and a phi prime bar to the k minus 1 on the right. Now, if this quantity is not equal to 0, then dividing both sides by it, I would get phi bar to the n over phi prime to the n is this ratio here, which depends only on k. So we're trying to come up with a relationship that holds for all n. So to be periodic, we need this to hold for all values of n. So how is it possible to have this change in quantity on the left equal to a fixed value here? Well, that certainly is a contradiction. So this implies that phi bar to the k minus 1 must be 0, and therefore phi bar to the k equals 1, and phi prime bar to the k also equals 1. So to be periodic with a period k right here, we need these two conditions to hold, and the smallest value of k satisfying that would just be the least common multiple of the order of phi bar and the order of phi prime bar. So we're brought back to studying orders of elements in a finite field, which is a cyclic group. The set of non-zero elements is a cyclic group. Now let's look at these particular cases here. If p is congruent to plus or minus 1 mod 5, then by quadratic reciprocity, since 5 is congruent to 1 mod 4, we can invert. P is congruent to plus or minus 1. And plus or minus 1, those are the two quadratic residues. So 5 is a quadratic residue which means we have a lambda in FP with lambda squared equaling 5. And so in this case, the square root of 5 symbol is an element of FP, and we get these two elements to belong to FP. So when I'm talking about the order of phi bar, we're really just talking about the order mod P of phi bar. And so we get that pi of P, the Pisano period, is the least common multiple of these two orders from our previous slide. In the second case, if P is congruent to plus or minus 2 mod 5, then by this same argument we did up here, 5P would be negative 1, and therefore 5 is a quadratic non-residue. So when we're looking for the square root of 5, it's not going to be an FP. We have to go to the quadratic extension. So phi bar and phi prime bar are in FP squared, but not in FP. So you'll recall that in FP squared, we've got an isomorphism where x is going to x to the p, and therefore these two conjugates are related. So phi prime is just phi to the pth power. So that's how you go from one conjugate to the other. You just raise to the pth power. And therefore, these two elements are going to have the same order. So the order of phi prime and the order of phi itself are equal. And you can either use the fact that these are conjugates, or just note that since this is a pth power, we have a formula for the order of an element raised to a power. And since p is relatively prime to p squared minus 1, these two things would have exactly the same order. Therefore, the formula we had in the previous slide, which was the least common multiple, well, these two numbers are identical, and so the least common multiple is just the order of phi bar in this case. Let's look at an example. Let's find the Pisano period for 11, pi of 11. So I want to look at the Fibonacci sequence mod 11. So this time 5 is a quadratic residue. 4 squared is congruent to 5. So 4 would be the square root of 5 in the formula. And the inverse of 2 is 6. 6 times 2 is 1 mod 11. So phi bar, the golden ratio mod 11, looks like this, which will be congruent to 6 times 1 plus 4, which is 30, and 30 is congruent to 8 mod 11. So phi bar is just 8, and its conjugate, we would look at 6 times 1 minus 4, which is negative 18, which is minus 7, which is 4 mod 11. Therefore, the nth Fibonacci number, mod 11, is just the inverse of 4, so that's the 1 over the square root of 5 right here, times phi to the n minus phi prime to the n. These should have been those barred terms. The inverse of 4 is 3, phi bar is 8, and phi prime bar is 4, so we get 3 times 8 to the n minus 4 to the n mod 11. And so you can see the periodic nature of Fn is determined by the periodic nature of the numbers 8 and 4 when you raise them to powers mod 11. So we get that pi of 11 is the least common multiple of the order of 4 and the order of 8. And this is just a little calculation here that the order of 4 is 5 and the order of 8 is 10, and so the least common multiple comes out to be 10. As a corollary of our previous theorem, we get the following. So pi of 2 and pi of 5, you just calculate those directly. But if p is congruent to plus or minus 1 mod 5, the Pisano period is a divisor of p minus 1. And if p is congruent to plus or minus 2 mod 5, then it's a divisor of 2p plus 2. And note, this is a big improvement over our original bound of m squared, where we could only say pi of p was less than p squared. So here the upper bound would be 2p plus 2 in the worst case. And, well, what's the proof? So part 1, you calculate them numerically. If p is plus or minus 1, then we saw that pi of p was the least common multiple of these two orders, but these are actually elements of fp star, which is a cyclic group of order p minus 1, and so the orders are always divisors of p minus 1. And therefore this least common multiple is going to be some divisor of p minus 1. If p is congruent to plus or minus 2, then the Pisano period is just the order of phi bar. And we saw in this case that the conjugate is just phi bar to the pth power. We also have that the product of phi and its conjugate is negative 1. That's the constant term in the quadratic. And so if you take phi bar to the p plus 1 power, this would just be phi times phi prime. So I'm just plugging in that phi prime is phi to the p power here, and we get phi bar to the p plus 1 is negative 1, and then squaring both sides, we get phi bar to the 2p plus 2 is plus 1, and therefore the order of phi bar is a divisor of 2p plus 2. Now let's look at a matrix point of view of the periodic behavior. So last time we saw that if you take this generating matrix 0, 1, 1, 1, then the nth power gives you the matrix of Fibonacci numbers. And if you take a to the n plus k power, you would get this matrix of Fibonacci numbers. And so if it is periodic mod m with fn plus k congruent to fn, that would mean that a to the n plus k is congruent to a to the n mod m for all values of little n. And this equation, since a is an invertible matrix, we just cancel out the a to the n power, and we get a to the k is the identity. So, determining the period of a Fibonacci sequence mod m is equivalent to determining the order of this matrix. What's the minimal value of k such that a to the k is the identity? Now when you're dealing with a matrix, we're actually living in a group here. So let's make the following definition. If A is an invertible n by n matrix over the ring Z mod m, then the order of A, denoted order mod m of A, is the minimal value of k such that A to the k is the identity matrix. So first of all, why should such an order exist? Well, we're living in a multiplicative group. So you're looking at the set of all invertible matrices over the ring Zm, and that's a multiplicative group. And it's a finite group because the entries have a finite number of elements. So, and we don't need to know its order, the set of all invertible matrices. And so therefore there will exist such a value of k. And what we had just observed in the previous slide then is the Pisano period mod m is the same as the order of this matrix mod m. So if we want to look at prime powers, so we started by looking at the Pisano period mod p, we would next go to prime powers, and let's do it from a matrix point of view here. So if p is a prime and a is an invertible matrix mod p, then I claim for any positive integer e, the order of the matrix mod p to the e is a divisor of p to the e minus 1 times the order of the matrix mod p. So in particular, the left-hand side is the Pisano period of p to the e, is a divisor of p to the e minus 1 times the Pisano period mod p. All right, let's see how we could prove this. So A is an invertible matrix. So I want to look at, let's give a name. Let's let K be the order mod P of A. So A to the K is the identity matrix. And then raise both sides to the pth power. So this means A to the K is congruent to I mod P. Let's go ahead and bring in congruence means it equals I plus P times some matrix B. Some matrix B whose entries are coming from, so it's a 2 by 2 matrix with entries that are integers, so M22Z, and then raise both sides to the pth power. So AK to the P is an I plus PB to the pth power, and we're just going to use the binomial expansion, and we get I plus P squared B plus P choose 2, P squared B squared, plus higher orders, and view this mod P squared, and we get that this is congruent to identity mod P squared. And you continue doing this. Raise again both sides, and we get AKP squared is congruent to I mod P cubed. And by induction, A, K, P to the E minus 1 is congruent to the identity matrix mod P to the E, and therefore the order of the matrix is a divisor of this quantity, QED. So that gives us this formula. The order of the matrix mod P to the E is a divisor of P to the E minus 1 times K, which is the order mod P. Okay, now let's put together what we've seen so far. So if I let M be an arbitrary positive integer with prime factorization, product of PI's to the EI's, then, and I want to look at the Pisano period mod M. We first observed that there's a Chinese remainder theorem type result. So having a periodic mod M is equivalent to saying Fn plus K is congruent to Fn mod Pi to the EI for all values of I. And therefore, the minimal value of K satisfying all of these relationships right here is precisely the least common multiple of the Pisano periods mod each of the individual prime powers. Okay, so that's step one. And then we observed on the previous slide that the Pisano period mod of prime power is related to the Pisano period mod P via this relationship. And we'd already studied the Pisano periods mod P. They're either a divisor of P minus 1 or 2P plus 2. And if you put all of this information together, these three facts here, you can deduce the following upper bound. That for any positive integer m, so this is for all m in the natural numbers, the Pisano period is bounded above by 6 times m. I'm not going to go through that proof, but you can challenge yourself if you want to work through those details.